Hello students, welcome back. Previously we studied images and preimages. The next topic, kernel. Here's a definition. Let phi be a homomorphism from a group G to another group G prime. The kernel of the homomorphism phi is defined as the preimage of the identity E prime of G prime. In other words, set of all elements of G, the domain, whose function value is E prime, the identity of G prime. And as you can see from this set builder notation, all the elements belong to G, so this is clearly a subset of G. But not only that, we actually claim this is not just a subset, but a subgroup. Is that clear? Well, let's go back to this expression. I use phi inverse of E prime like that, but this expression can be a little bit misleading. It's actually an abbreviation. The inverse map phi inverse may not exist. If phi is bijection, then yes, inverse map exists, but otherwise it doesn't. What do you mean by this? This is actually a shorthand of this. Remember, the preimage applies to the subset of the target. And in a special case, when the subset is a singleton, then we express without this brace like this as an abbreviation. But starting set is kind of like this. And then what is this? This is a trivial subgroup of G prime. And remember the property of the preimages and images here, especially this one. Both images and preimages of homomorphisms preserve the subgroup structure, especially here. If H prime is a subgroup, then its preimage is a subgroup of G. Here in this case, E prime, that's a trivial subgroup of G prime. So its preimage must be a subgroup of G as well. As for the proof of that, we already went through that here. All these identity inverse and closeness. So we are not going to redo that here. And indeed, that's a claim and that's a proof. Just a one-liner. It's a preimage of a trivial subgroup, so it's a subgroup. But just for an exercise, let's do a direct proof. So this direct proof is not necessary, I understand, but as an exercise, let's just do it. Also, imagine a situation that I write this kind of problem in exam or homework. Proof directly from the definition. In that case, you have to do it this way. We have to prove these three. Closed under the group operation, identity, and inverse. What do you mean by closed under the group operation? Get any pair of elements from the kernel. I mean, these are too confusing, so let's go back to the original expression. Yeah, okay. Yeah, choose two elements from here, and then apply the group operation. It has to be back in this kernel. That's what you have to prove. And then the identity exists. That's going to be rather trivial. You'll see the identity exists, in other words. And then the inverse. Similar, I just select one element, and how about its inverse? That's what you have to prove. So these three. Which is the easiest? Well, of course, this one. So what do you mean by something belongs to kernel? That means the function value of that something is E prime. So this means that question, is this true? So something belongs to the kernel means phi of that something is E prime. So E belongs to kernel, that means phi of E is E prime. Is this true? Of course it is true. We already proved that way back in section 1. Homomorphisms preserve the identity and inverse and also the group operation. So E belongs to kernel because phi of E is E prime. Okay, that was easy. Next easiest, the inverse. Here we have to consider 2 elements. Here I have to consider only 1 element. So okay, how do I prove that? What do you mean by x belongs to phi? What do you mean by x belongs to phi? That means phi of x is E prime. Remember that? That's the definition. Something belongs to the kernel means phi of that something is E prime. So this blue and that blue are equivalent. How about this one? The same. Let's choose green. And then phi of that x inverse is E prime. Oops. And this green and that green are the same. And instead of trying to prove this, we can try to prove this. And is that easy? Yeah, it's easy because phi preserves the inverse structure. So phi of x inverse is the inverse of phi of x, like this. Phi of x inverse is the inverse of phi of x. So we have E prime inverse, so it's E prime. Consequently, we get what we want. X inverse belongs to the kernel. This is actually the technical part that corresponds to this dot dot dot. But really important observation here is to make this transition blue to this blue. If you do that, and then doing the same thing, green to this green, that follows immediately. It's the same thing, if you get that idea. And of course, you have to go back to this definition. So whenever you have something belong to kernel, you can automatically rewrite it as phi of that something is E prime. That's what I did for blue and also green. And once I do that, connecting those like this, highlighted in red, is not too bad. So the highlighted part, the red part, may be the technical part, but the reduction part is actually much more important. How about this? Well, let's do the same thing. Let's reduce this one. X belongs to the kernel. What do you mean by that? That means phi of x is E prime. But then again, y also belongs to kernel. So phi of y is also E prime. In short, this blue and that blue are the same. As for this one, again used the property of the kernel, that definition. Xy belongs to kernel, that means phi of that xy is E prime. So phi of x times y is E prime. And let's highlight this in green and this one in green. And please note this green and that green are equivalent. So instead of trying to prove this one, you can prove this. Can you prove that? Well, looks like all you have to do is to use this property of the homomorphism. phi of xy can be decomposed into phi of x and phi of y. Like this. Phi of xy is phi of x and phi of y, which is e prime times e prime, and that's e prime. Therefore, phi of xy belongs to the kernel. So this red part, that's where I use the property of the homomorphism. So that's arguably the technical part that goes to this dot dot dot. But as I mentioned before, making this transition, rewriting the definition of kernel into this blue and equivalently like that, that's the hard part, and that's the important part. Once you make that transition, everything else is going to be easy from that point on. And remember this technique because we're going to be using this whenever we have kernel. And that's where we're going to conclude the first video on kernel. And we're going to come back and discuss more about kernel in the next 2 videos, I think. Next one, or I think it's going to be next 2 videos. So total 3 videos on kernels.